Dear students, friends and learners, I am Dr. Shashank Shrivastava from SOET in the Gandhi National Open University. So I took a lecture on the mechanical properties of materials. Before this, we have discussed up to the stress strain diagram of the tensile of the ductile materials, and now onwards we will discuss the stress strain diagram of the brittle materials. So the brittle and the ductile materials I have explained to you earlier, and so we discussed now the stress strain diagram for the brittle materials. So here also there are two kinds of brittle materials, type A and type B. So the type A one, like the cast iron one, it will also have the ultimate tensile strength like we have in case of the ductile materials, and they also show a linear relationship between stress and strain. The type B1 materials like the concrete, they do not show a linear relationship between stress and strain, and the maximum stress sustained by such material is defined as the ultimate tensile strength. So from here you can see in the figure, here are the two types, type A and type B. So for the type A, you can see the yield point, the elastic limit, the limit of proportionality, all the things are there, like in case of the ductile materials. But the difference from the ductile material is that it is not going to that point like ultimate tensile strength and then further going down to the fracture point. It is fracturing much before than that. In the type B, you can see there is nothing like yield point, elastic limit or limit of proportionality, only it will fracture, and that is the case of like concrete. After discussing the stress strain diagram for the brittle materials, let's move back again to the stress strain diagram for the ductile materials, where we shall discuss the elastic plastic deformations and the elastic plastic strains. These are very important because they are helpful in defining certain properties, mechanical properties, which we are now going to discuss. Plastic unloading follows a curve which is somewhat parallel to the original elastic line. So we see here that the original elastic line was a linear line. So when we do the plastic unloading, then also it follows the same path, but that strain, the remaining residual strain, will always be there when we have reached the plastic limit. So when a specimen is fully unloaded to point G, some strain still remains in it. The residual strain is the plastic component of strain. A part of the strain between F and G has been recovered, and this is an elastic part of strain at point F and denoted by EE in the figure. On reloading the specimen from point G, curve follows a path very close to unloading curve and eventually joins the original curve at H. The area between loading and unloading curve, which is shown as hashed in the figure, represents the loss of energy due to unloading cycle and is termed hysteresis. So here you can see in the figure, the first one is about the elastic plastic deformation and the second one elastic and plastic strains. So the first one you can see, same stress strain diagram. OA is the linear portion, A to D, from A onwards yield has occurred, so plasticity has come in, up to D, D means the ultimate tensile strength, so ultimate stress, and up to A, from A to D, this deformation is happening. And from D onwards, you can see that the stress is coming down, whereas the strain is still taking place, and it is taking you up to a point E where final fracture takes place. That means the final fracture takes place at a stress lower than the ultimate stress. So in the figure B, you can see elastic and plastic strains. Here what we are doing is that the original yield point or the limit of proportionality end or the elastic limit end is point A. And if we do initial loading even after point A, then what will happen? It will go up to a point H. And you can see from here, when we start unloading from here, it will follow a path, curve, a certain curve, and it will come down to the point G. But a residual strain remains in this case. You can see from this figure, epsilon p it is given, and when we reload it again, then it follows a path, but this path is different than the first one because the yield point now has changed. So this hashed thing in the figure is known as the hysteresis loss. So now we start discussing different kinds of properties which we got from the simple tension test. Mechanical properties. The first one is the modulus of elasticity, or it is also known as the Young's modulus. And mathematically it is also given by force upon area divided by the strain, meaning delta L by L. F by A by delta L by L is also known as the modulus of elasticity or the Young's modulus. And you can see here, modulus of elasticity is the ratio of stress and strain when there is a linear relationship between the two. That means we are talking only about the elastic limit. We are not going beyond that point, the limit of proportionality and the elastic limit. So that's why it is known as the limit of proportionality, because the stress is directly proportional to the strain. So you can see the sigma is given, the epsilon is given. Sigma represents the stress, epsilon represents the strain. And when we connect both these, because they are directly proportional, so sigma becomes equal to E into epsilon. And this E here, the capital E, is known as the Young's modulus, given by sigma divided by epsilon. So slope of the elastic part of a stress strain diagram gives us the modulus of elasticity. But this is not a very reliable method since it involves deformations during loading. There are certain kinds of deformations, so we cannot say that this will always be linear and we can get the modulus of elasticity just by taking the slope. This modulus of elasticity is constant for a given material, meaning it's a material property. It will not vary by a small addition of alloying contents. It will not vary like that. And whereas the stiffness is also there, stiffness is related to Young's modulus, but it is also dependent on the geometry of the material. So that's now the second property we are going to discuss. The first we discussed the modulus of elasticity. The next one is the yield strength. So the yield strength represents the transition from elastic to plastic behavior of the material. Again, the same thing which I discussed during the explanation of the stress strain curve, that during elasticity, when we are applying some load on the specimen, on removal of that load, the material will come back to its original position. But in case of plastic behavior, the material will not come back to its original position. Instead, it will have a certain residual strain. Actually, there are ideal and practical elastic strengths. Both proportional and elastic strengths represent ideal strength, and the ideal values are seldom used. They are not frequently used for material characterization as they are difficult to determine. Obviously, we know anything ideal is not that easy to get. So the figure that will be coming up will show the yield of mild steel and the structural steel. And from there we can see that total deformation during yielding is 10 times more than deformation up to the elastic limit. So there are two yield points, the upper and the lower. So this difference exists as explained in the earlier portion also. It exists because movement of the ends of the specimen as produced by two machine cross heads does not proceed as fast as the yield deformation of the material. So from the figure here, I will just explain to you what is happening. Like you see, it is strain in the x-axis. You see from 0 to 0.002 millimeter per millimeter. You can see this curve is somewhat linear, more or less linear. And this strain, actually, the deformation here is about 1/10 of the deformation that is taking place after yield. And that portion is represented by the portion from C to E. So that is about 10 times strain that the portion of the elastic limit. So here it is, and the second curve you can see, it is showing that there are two yield points, the higher yield point given by C and further lower yield point given by D, represented by D. So there are two yield points, and the reason I have mentioned earlier why it takes place. So after discussing the elasticity, Young's modulus and yield strength, next we move on to the definition of ductility. So if a material can be drawn into wires, then it is said to be ductile, meaning it has larger amount of deformation before fracture. That's what it is given here. There is considerable deformation in the plastic zone that leads to ductility. After the elastic zone is over, then in the plastic zone the deformation will be high in case of ductile material, whereas in brittle material it will not be high. And this deformation can be used as a measure of ductility. So the total deformation suffered by a specimen up to fracture divided by the original length. That means the length between the gauge points. As discussed earlier, the gauge length was the distance between 2 points marked on the specimen. So if it is multiplied by 100, this is known as the percentage elongation. Percentage elongation is the reference for indicating the ductility of the material. However, percentage elongation depends on what gauge length is taken. So here again, how this necking and all is taking place is given in this figure. The sequence of deformation of a cylindrical specimen with reference to different points, just before point A, just before point F, and then just after point F and at point G. So this is how the material is changing its shape while it is being subjected to the load. This is about the gauge length. You can see the specimen here and different points are marked here. So according to the points which are taken, the gauge length can vary. So it has to be standardized then. So we can see from the figure that different gauge points have been marked on the specimen. We can also see that by choosing different gauge points, the percentage elongation shall also differ from that of a different set of gauge points. So suppose I take the inner two gauge points from both the sides, then that elongation will be different from the 2 points which are at the outermost part. So that's what it means, that the gauge length can vary depending upon the point which we are choosing. So it indicates that percentage elongation is not a unique quantity but varies with gauge lengths. Thus gauge length needs to be standardized so that comparison of ductility of two materials can be done consistently. So if there are two materials, suppose there is steel and suppose there is aluminum, then if we have to measure the ductility of those two materials, then we have to take the standard gauge length. Otherwise the gauge length will keep on varying. So there are methods for determining the percentage elongation, and one of the method is to measure the strain at the time of fracture from the stress strain diagram, like the point which was mentioned, the point E in the diagram where fracture took place. From that point to the origin, if we measure and multiply it by 100, then it will give us the percentage elongation. But more practical way is there. What is that way? That is to get the fractured specimen, or the two pieces have come out after the main specimen has broken. So it has broken into two pieces, and we can match these two pieces end to end and measure it with the help of some measuring device, whether it be vernier calipers or any other thing. We can measure the total length. So the total final length will come. Then what we can do, we can subtract from it the original length of the material, the main specimen, and divide by the original length and multiply it by 100. So it will give us the percentage elongation. Similarly, we have seen that there is elongation, so there has been a reduction in area as well. So this ductility can also be represented in terms of reduction in area. So percentage reduction in area can be given as A0 minus AF by A0, where A0 was the original cross-sectional area of the specimen and AF is the current cross-sectional area of the specimen after the necking and fracture had taken place. So we have discussed up till now the Young's modulus, the ductility, yield strength. So now we discuss the toughness. What is the toughness? It is the ability of the material to absorb energy during entire elastic and plastic deformation. So any material is there, and if it is being loaded, then it is absorbing certain amount of energy. So that energy is being given by toughness. So modulus of toughness is denoted by the area under the stress strain curve and is the energy absorbed by the material of the specimen per unit volume up to fracture. So there's a mathematical proof also for that. Suppose if a load P is acting upon the specimen and it causes a displacement, a small displacement, say dl. It is a very small displacement. Then work done we know is given by force into displacement, and we are doing the integral of P into dl because we are taking a small infinitesimal elements, so we have to sum up all those. So here you see U is this work done, and if we are dividing it by the original area of cross section and the original length, then what we are getting actually, we are getting the this work done per unit volume. And in the other side also, the right hand side of the equation also changes. P into dl, integral of P into dl divided by A naught L naught, and thereafter what we get from this, we get integral of sigma into d epsilon. Because why it is happening? Because as described earlier, P by A naught is sigma, that is stress, and dl by L naught is nothing but strain. So it becomes the integral of sigma and d epsilon. So this is a proof. That means this integral is giving us the area under the stress strain curve. So that is what is toughness. Work done upon the specimen per unit volume during stretching, which is stored in the specimen as strain energy, can be measured as area under the curve and is known as toughness. Next we come to the property of resilience. We discussed toughness and now we discuss resilience. So what is resilience? It is the maximum energy that material can absorb without attaining plastic state. That is called resilience. So in case of toughness, we went beyond the elastic limit and went up to the fracture point. Whereas in this case, we are only going up to the elastic limit. So that is the difference between resilience and toughness. So modulus of resilience, how it is defined, it is the maximum elastic energy per unit volume that material can absorb without attaining plastic state. And modulus of resilience, it is given by half into sigma y into epsilon y. Let me explain what is sigma y and epsilon y. Sigma y is the yield stress. Because it is not going into the plastic region, that's why only up to the yield region. So sigma y is the yield stress, and epsilon y is the strain up to that point, corresponding to the point of stress. So there's a triangle, and this area of a triangle is given by half into length into base. So half into sigma y into epsilon y. This is called the modulus of resilience. And since epsilon y is given by sigma y upon E, the relation which we discussed just before this one, so MOR, that is modulus of resilience, becomes sigma square y by 2E. Sigma square y, again sigma y is the yield stress and E capital E is the Young's modulus. So the MOR can be given in terms of yield stress and modulus of elasticity. So here is the comparison between the difference between the toughness and the resilience. So it is given here with the help of the curve. You can see this curve. One is the lower curve is going up to the fracture limit, whereas the upper one is going to the yield point only. So the triangle, that hashed triangle you are seeing, is about resilience, and the other one, the lower one, is about the toughness. So there are certain materials in which we require higher toughness, and certain places we require higher resilience. Like here it is mentioned, like in gears, chains, hooks, freight car coupling, etc., we need higher toughness, meaning that material should absorb more amount of energy before fracture. It should be of that much strength. Whereas in case of a spring, what will happen? We need higher resilience because we don't want the spring's length to change actually. So the difference here is given between the toughness and the resilience. Again, I am telling you so that you can get the point. The modulus of the toughness will depend upon both the ultimate tensile strength and strain at fracture. So it is dependent on both ultimate tensile strength and the strain corresponding to that. Whereas modulus of resilience is dependent on the yield strength and the stress and the strain corresponding to that. So that is the difference between the two, and more ductile material means more toughness and higher yield strength means more resilient. So now let's discuss about strain hardening. what is strain hardening? Let's refer to the figure which is given here. It is showing about the strain hardening. So it was stated that on reloading from G, the new curve joins the original curve at H, where point H is higher than point A. So we are going beyond the point A. Earlier it was at A, the yield point. Now it is going beyond that. In other words, it can be said that due to the initial loading of the specimen up to point F, its yield strength has increased to H, and if it were not so, then the reloading curve must have followed a path similar to the original curve, showing a yield strength equal to the height of point A. So now we discuss about fracture in tension. So there's a difference between the ductile materials and the brittle materials when fracture is happening. So in case of ductile materials, we see that they are not too weak and ultimately they fail after resisting considerable amount of load. They are more weak in shear than in tension. Whereas in case of brittle material, they are weak against tensile stress and they fail very quickly. And the maximum shearing stress is along a plane 45 degree to the axis, so it should fail along that. But due to the necking, the state of stress varies, so it may be possible that it does not fail along the 45 degree axis. And the brittle material, it fails along a cross section on which maximum tensile stress is acting. In case of ductile material, what is the shape after breaking? It is like a cup and cone, and they match at an angle of 45 degree with the axis, showing that the final fracture has occurred along these planes all around the periphery. And the tensile stress in case of brittle material is uniformly distributed over any cross section. In case of ductile materials, there are lines on the surface of the yield point along which the atomic planes slide due to maximum shearing stress, whereas in case of the brittle material, surfaces of the fracture has granular appearances. So here we see the AA figure is the tension specimen itself, and the B1 is the state of stress at any point with respect to the XY axis. There are two axes we are seeing here in the figure, X and Y. So it is giving the state of stress. And Y axis is parallel to the axis of the specimen in case of the figure B. In case of figure C, state of stress with respect to X dash Y dash axis when an angle 45 degree with respect to the axis of the specimen. The maximum shearing stress equal to B by 2A, and this acts parallel to the X dash Y dash axis. So here are three different figures. The first one is telling about the tension specimen, and the other two how this material is going to break at which angle and along which axis. So here is the thing which we discussed earlier, that how the ductile material fails. It will be more clear here with the figure, and how the brittle material fails. So you can see here the first figure, the A1, the cup is there. You can see a cup type thing and a cone. So this thing happens in case of the ductile materials, and you can also see in the hashed version that there are lines. So lines will remain on the specimen after breaking. Whereas in case of the ductile materials, you see there is nothing like cup and cone. They have simply broken across the cross section. There is no distortion there in that portion. They have simply broken, and you can also see granular things are there. So that is the difference. In case of ductile, there are lines, whereas in case of brittle, the granular portion is there. So after discussing this toughness, resilience, and the breaking of the ductile and brittle materials, what happens during fracture, we are now discussing true stress and true strain. So this thing is very important actually, because earlier we have done all our analysis with respect to the engineering stress. So what is true stress? True stress at any point in the tension test specimen is defined as the ratio of load to corresponding area of cross section, or the current area of cross section. That is the difference between the engineering stress and the true stress. In the case of true stress, always the area which is at that particular time is being taken. It's not the original area of cross section. And true strain also is like that. it is defined as some summation of the incremental strain over the entire load range from 0 to P. If the initial length L0 changes to length L during load change of 0 to P, true strain will be given by the integral of dl by L. Because we are taking infinitesimal elements, so we have to sum them up in integral form, because we have to get that portion, the changes in every portion, we have to get all those things, because change is taking place, it is taking place slowly, but it is taking place, and we have to record all those things when we are talking of true stress and true strain. So because of the final form of the true strain, it is also known as logarithmic strain. So here is the diagram. You can see, if we take the true stress strain diagram, it will look like this one. Earlier we saw that after coming to the stage of ultimate stress, the stress goes down, but that is not the reality, because in that case we were taking the original area of cross section, so the stress was going down. But in reality what happens, the neck has formed and the material is almost going to break, the area of cross section is almost reduced to 0, so the true strain in reality will keep on, true stress in reality will keep on going higher and higher. So that is reflected by the line that is going towards the infinity, and it is showing no end there. So that is the true engineering, true stress, that it is different from the engineering stress in that way. So in this lecture you saw that we discussed about the various mechanical properties of a material and how it fractures, and how the ductile material and the brittle material fractures. All these things were discussed in this particular lecture. Thank you.